Welcome to our video presentation on fraud detection. Banks and card companies were able to prevent the loss of £1.6 billion of unauthorised fraud in 2020. This is largely due to the increasingly sophisticated machine learning models which are used to prevent them. Still, fraud detection presents an interesting challenge due to the class imbalance. In a typical database of credit card transactions, for example, we see that most transactions are authentic, only a very small percentage of them are flagged as fraudulent. From a technical perspective, this means that any learning-based algorithm has a very small subset of data with which it can build an interpretation of a fraudulent transaction. This report covers the use of several contemporary machine learning models to classify fraudulent transactions on a sparse dataset provided by Kaggle. We give particular attention to the techniques which tackle imbalanced datasets and the complications which can arise from them.
When dealing with credit card information, ethics and privacy are of the utmost importance. Our dataset has undergone Pca Transformation, which is a dimensionality reduction technique that combines pieces of data to try to make sure we still have the information of the underlying dataset while hiding the actual elements. This meant our dataset was represented by 30 elements, v1 to v28, and then the time and the value of the purchase. Therefore, the only ways in which our data was changed was for certain graphs we changed the time units from seconds to hours, so visualizing it was easier. When exploring the actual data, we need to look at the fraud transactions, being only 0.17% of the data. Finding these fraud processes correctly is the gauge on which our project's success will be measured. As our data has gone under Pca Transformation, it was harder to analyse the data, so we started by looking for patterns within our named elements, these being the time of purchase and the price attached to the purchase. The table in the top left shows the distribution of the transaction amount of each class. As you can see, all of the fraud values sit within the minimum and maximum values of the regular purchases. We can also see the mean values are within the standard deviation of each other's means. This means that we cannot accurately pick out the class of each piece of data using this comparison. Similar cases shown when looking at the time values in the bottom left. Here again the data is well mixed. Plotting the time against the purchased amount shows how well our classes are integrated. Therefore, we will need to use a more complicated model, including the v-named features, to split this data apart. Looking at each particular v-named feature, we see their values overlap for features like v15 and v22, while some features like v14 and v17 show a more significant variation between the classes. Therefore, when we created the models, the features with the greater variance had a greater weighting on classifying a piece of data.
When we came across this project, a big challenge when detecting instances of fraud is trying to deal with imbalanced datasets. An imbalanced dataset is one where there's an unequal class distribution, and we know majority of transactions that take place are usually non-fraudulent, with a very insignificant amount being fraudulent. For example, one of the datasets we had, 99.83% of the transactions were non-fraudulent and 0.17% being fraudulent. As the data is very skewed, applying any modeling tools to the data as it is will lead to overfitting. However, there were several approaches we could have used on this dataset to tackle this problem. We decided to go for undersampling and oversampling, as these were the two most common solutions that we had seen when dealing with imbalanced datasets. Undersampling involves reducing data from the majority class, while oversampling involves duplicating the minority class in order to have a more balanced dataset. We decided to go with undersampling and oversampling as they were very accurate when detecting fraud cases, with both of them having over 90% accuracy.
We apply 4 common classifiers in undersampling and choose the optimal performance to carry on oversampling method. The classifiers are logistic regression, k-nearest neighbor, support vector machine, and decision tree. We also use cross-validation for a better indication of how well our model will perform on unseen data. In table, we can see logistic regression have the highest score, but all have very close score. So if we take a look at confusion matrix here, we can see some closer difference. Top left square and bottom right square represent the number of correctly classification of the no class and yes class. Decision tree have no false negative, however it have the most false positive cases. Logistic regression have 3 more true positive cases comparing to support vector classifier, and KNN have a bit more false negative compared with others. In oversampling, we use smooth function carry on with logistic regression classifier. The accuracy score it got is much higher compared with undersampling. We compute the average precision record and the graph clearly show the differences. An ideal system with high precision and high recall will return many results with all results labeled correctly. In oversampling one, while recall is around 0.75, the precision can still stay 0.8. However, in undersampling, when recall is around 0.3, the precision gets lost over 0.8 movement. From the result we get, we can say oversampling is a better choice for fraud detection. Since undersampling will draw samples, it might be the reason causing lower accuracy rate.
Outlier detection is the process of finding data objects with behaviors that are very different from expectation. After the data frame has been correctly balanced, we removed extreme outliers from features that have a high correlation with our classes. This will have a positive impact on the accuracy as the model will be more effective in predicting data points. However, we have to be cautious when removing outliers as we might increase the risk of information loss, which could increase the chance of underfitting and as a result cause a model to have a lower accuracy.
We are quite fortunate to have a corpus of Kaggle solutions to the dataset we've chosen. These solutions cover nearly all feasible data pre-processing, exploration, modeling, and class imbalance techniques available to a data scientist. This is a double-edged sword, however. Since we have access to these well-implemented approaches, the challenge becomes finding the most effective methods whilst also maintaining a sense of novelty in our findings. To solve this challenge, we have focused much of our efforts on critically evaluating these solutions, determining what they do well and how they could be improved upon. We note that many Kaggle solutions are largely focused on quantitative metrics with less regard for the more qualitative implications of the specific problem. We have examined numerous implementations and we hope to construct a narrative which acknowledges the factors relevant to our stakeholders' LV. Thank you for listening. Boom! That's that one done. Cheers, Brandon.